There is a question that sits quietly beneath everything you have ever touched. Every stone, every breath of air, every atom of your own body, all of it should not exist. Welcome to the Sleepy Lab. Tonight, we drift through one of the deepest mysteries in all of physics, the story of matter and antimatter, and the razor-thin imbalance that made the universe possible. If you find this kind of quiet wonder helpful for sleep, consider subscribing, one sleepy soul at a time. Now, let's begin. In the very first moments after the Big Bang, the universe was not yet a place. It was a condition. Unimaginably hot, unimaginably dense, a state of energy so extreme that the distinction between something and nothing had barely begun to form. And within that first fraction of a second, a sliver of time far too small to name easily, something remarkable happened. Matter appeared. But it did not appear alone. For every particle of matter that flickered into existence, a mirror particle appeared alongside it, its opposite in almost every way, and yet identical in mass. These were antiparticles, and together, matter and antimatter filled the newborn universe in nearly equal measure. Nearly equal. That word, nearly, is the reason you are here tonight. When a particle of matter meets its antiparticle, they do not simply collide and scatter. They vanish. Both of them, entirely converted into pure energy. No debris, no remainder, just a burst of light, and then nothing where two particles once were. In those first moments, this was happening everywhere, continuously, on a scale that has no comparison in anything that came after. A vast, mutual cancellation, matter and antimatter consuming each other in an endless, symmetrical fire. And if the balance had been perfect, that would have been the end of the story. The universe would have annihilated itself completely. No atoms, no stars, no dust drifting between galaxies. Only light, a cooling sea of photons spreading outward through empty space, with nothing else to show that anything had ever tried to exist. But the balance was not perfect. For every billion matter-antimatter pairs that found each other and disappeared, there was one extra matter particle. Just one. One particle in a billion that had no mirror twin to cancel it. One particle that survived. And that remainder, that tiny, improbable surplus, is everything. Every star burning in the night sky, every planet, every ocean, every mountain, every cell, and every living thing that has ever existed on this world. All of it is the leftover fraction, the 1 in a billion that was not canceled out. Antimatter, it is worth saying quietly, is not a concept that lives only in equations. It is real. It has been detected. It has been created. It has been held, briefly, in laboratories built for exactly that purpose. The story of how we came to know this begins not with a large machine or a grand experiment, but with a single photograph. It was 1932. A physicist named Carl Anderson was studying cosmic rays, high-energy particles that fall continuously from space, passing through the atmosphere and into his instruments. He was using a device called a cloud chamber, a sealed container filled with supersaturated vapor, in which a passing charged particle leaves a faint, visible trail like a tiny contrail in a miniature sky. Anderson placed his cloud chamber inside a magnetic field. Charged particles, when they move through a magnetic field, curve. The direction of the curve tells you the sign of the charge. Negative particles curve one way, positive particles curve the other. And one day, Anderson saw a trail that curved the wrong way. Not wrong in the sense of an error, wrong in the sense of unexpected. The trail had the weight of an electron. It was light, delicate, exactly the right curvature for something with an electron's mass, but it bent in the direction of a positive charge. He had found a particle that should not have existed. A positron, the antimatter twin of the electron, equal in mass, opposite in charge. The first antiparticle ever observed by human eyes. What makes this discovery quietly extraordinary is that someone had already predicted it. 4 years earlier, in 1928, a British physicist named Paul Dirac was working on a problem in theoretical physics. He was trying to write an equation that described the electron in a way that was consistent with both quantum mechanics and Einstein's special relativity, two frameworks that, at the time, did not sit easily together. His equation worked. It described the electron with a precision that had not been achieved before. It predicted the electron's behavior, its spin, its interaction with magnetic fields, all of it, emerging from the mathematics with quiet inevitability. But the equation had a feature that Dirac could not simply ignore. It had two solutions. Every equation of this kind can, in principle, have multiple solutions. Often the extra ones are discarded as mathematical artifacts, answers that work on paper but correspond to nothing physical. Dirac considered that possibility. But the second solution was too structured, too internally consistent to dismiss. It described a particle identical to the electron in every measurable way, except that its charge was positive. Dirac sat with this for a time. He eventually concluded, carefully, that the mathematics was telling him something true, that if the electron existed, then a mirror particle of opposite charge must also exist, somewhere, waiting to be found. He published this in 1928. 2 years later, Carl Anderson found the trail in the cloud chamber. The mathematics had seen it first. There is something worth resting with in that. A man, working alone with equations, found a reflection of reality that no instrument had yet detected, not by guessing, not by intuition alone, but by following the internal logic of the mathematics wherever it led, even when it led somewhere strange. Dirac's equation did not merely describe the electron. It implied that the universe had a kind of symmetry built into its foundations, that for every particle, there was a corresponding antiparticle. That matter, as we know it, was only half of something larger. And when Anderson's photograph confirmed it, when the curved trail appeared in the vapor and matched the prediction exactly, it meant that this symmetry was not just mathematical. It was physical. It was real. And yet, if that symmetry were perfect, if matter and antimatter were truly equal partners in every way, then the universe we live in could not exist. The fact that you are here, breathing slowly in the dark, drifting towards sleep, is evidence that the symmetry broke somewhere, somehow, in the first fraction of a second after everything began. One particle in a billion survived. And from that survival, across billions of years, came everything. The stars formed from it. The planets condensed from it. Life assembled itself from it, slowly, patiently, across timescales that are difficult to hold in the mind. And now, here you are, made of that ancient remainder, lying quietly in the dark, at the end of a very long chain of events that began with an imbalance too small to see. Rest in that for a moment. You are not separate from the universe's story. You are one of its oldest consequences. And Dirac's equation said something else, too. Something that took a moment to fully absorb, even for the people who first read it. The equation described the electron with extraordinary precision, its energy, its spin, its behavior in electric and magnetic fields. All of it fell out of the mathematics naturally, without being forced in. But the equation had two solutions, not one. When Dirac solved it, he found that the mathematics permitted a second kind of particle, identical to the electron in every measurable way, except for one thing. Its electric charge was reversed. Where the electron carried a negative charge, this mirror particle carried a positive one. For a time, Dirac was uncertain what to make of it. Some physicists suggested the second solution was simply a mathematical artifact, something the equations produced but nature did not. But the equations were too precise for that. They had already described the electrons so accurately that dismissing half of their output felt like a kind of willful blindness. And so, the prediction stood. A mirror particle must exist. And 4 years later, in a cloud chamber in California, it did. What Dirac had found, without knowing it, was not just a new particle. He had found a principle, a deep structural feature of the universe, written into the mathematics of quantum mechanics and relativity together. Every particle, the equations implied, has a counterpart, a twin of equal mass and opposite charge. And when those twins meet, they do not simply collide and scatter the way billiard balls might. They do not slow each other down or deflect each other's paths. They vanish. Both of them entirely in the same instant. What remains is not matter. It is not even the debris of matter. It is pure energy, released in a burst of light so energetic that ordinary light cannot compare. This is annihilation, and it is one of the most complete transformations in nature. When a particle meets its antiparticle, every bit of their mass is converted into energy. Not most of it, not a large fraction of it, all of it. There is no remainder. Einstein's equation, the one that relates mass to energy through the speed of light, describes this conversion exactly. E equals mc squared. The mass disappears, and in its place comes energy equal to that mass multiplied by the speed of light, multiplied again by itself. The speed of light is a very large number. Its square is larger still. And so even a tiny amount of mass, when fully converted, releases an enormous amount of energy. This is what makes annihilation so different from anything in ordinary chemistry, or even in nuclear reactions. In a chemical reaction, only the outermost electrons rearrange. The mass of the atoms is essentially unchanged. The energy released comes from the reorganization of bonds, not from mass itself. In a nuclear reaction, fission or fusion, a small fraction of the mass is converted to energy, a few tenths of a percent, roughly enough to power cities or to level them. But in annihilation, the conversion is total. 100% of the mass becomes energy. Nothing is held back. A single gram of antimatter, meeting a single gram of ordinary matter, would release roughly the energy of a large nuclear weapon from 2 grams of material. The efficiency is unlike anything else we know how to do. That energy does not emerge as heat or as a pressure wave or as visible light. It emerges as gamma rays. Gamma rays are electromagnetic radiation, the same family as radio waves, and visible light, and X-rays, but at the far extreme of the spectrum. They carry more energy per photon than any other form of light. They pass through most materials as though those materials were barely there. When matter and antimatter annihilate, the energy that was once locked inside their mass radiates outward as gamma rays, moving at the speed of light in every direction. In the early universe, this happened continuously, everywhere, for the first fractions of a second. The entire cosmos was a sea of annihilation, of matter and antimatter meeting and dissolving into light. And then it stopped? Because the antimatter ran out, or nearly ran out. What remained was the small surplus, one particle in a billion, that had no partner to meet. And from that surplus, everything was built. But the story of antimatter did not end there. It continued, quietly, in ways that are easy to overlook. The universe still produces antimatter. Cosmic rays striking the upper atmosphere generated. Certain radioactive isotopes produce it as they decay, and the human body, without any intervention, generates a small and steady trickle of it. Some of the isotopes naturally present in bone and tissue, carbon-11, oxygen-15, potassium-40, undergo a form of radioactive decay in which a proton converts into a neutron and releases a positron in the process. That positron, the antimatter twin of the electron, travels a very short distance through the surrounding tissue, about a millimeter, on average, before it meets an ordinary electron, and annihilates. The two gamma rays produced by that annihilation fly outward in exactly opposite directions, precisely 180 degrees apart. This is a consequence of conservation of momentum. The two photons must balance each other exactly. In this predictable geometry, two gamma rays, always opposite, always at the same energy, turns out to be extraordinarily useful. Hospitals use it. A PET scanner, positron emission tomography, works by introducing a mildly radioactive compound into the body, one that emits positrons as it decays. The compound is designed to accumulate in tissues with high metabolic activity, tumors, for instance, or active regions of the brain. As the positrons annihilate with nearby electrons, the scanner detects the paired gamma rays. Because the two photons always travel in opposite directions, the scanner can calculate precisely where along that line the annihilation occurred. By collecting many such events from many angles, it reconstructs a three-dimensional image of where the radioactive compound has gathered. The result is a map of metabolic activity inside a living body, a way of seeing not just structure, but function, not just where the tissue is, but what it is doing. And the tool that makes this possible is antimatter. Not antimatter as an abstraction, not antimatter as a theoretical curiosity from a physics textbook, but antimatter produced inside the body, traveling a millimeter, annihilating, and leaving behind a pair of gamma rays that a machine can read. There is something quietly remarkable about this. The same phenomenon that governed the first fraction of a second of the universe, matter meeting, antimatter, mass dissolving into light, is happening in miniature inside hospital rooms every day. The physics is identical. The scale is different by many orders of magnitude, but the process is the same. Annihilation, put to use. The universe's most complete transformation, harnessed gently to help a physician see inside a patient who is lying still, breathing slowly, waiting. Not so different, perhaps, from lying still right now, breathing slowly, letting the mind grow quiet. The same particles that shaped the first moments of everything are part of you, moving through you, occasionally meeting their opposites and dissolving into light, in the dark interior of your own body, without your awareness, without any sensation at all. Quietly. The universe still doing what it has always done. And this has been happening inside you your entire life. Not occasionally, not in rare circumstances, but continuously, as a quiet consequence of being alive. Certain atoms in the body are naturally unstable. Isotopes of potassium, of carbon, of other elements woven into bone and tissue. They decay slowly, releasing particles as they shift toward more stable configurations. And among those particles, sometimes is a positron. Not a positron created in a laboratory, not one steered by magnets or coaxed from a particle accelerator, but one produced by the ordinary chemistry of a living body, in the dark interior of a bone or somewhere deep in soft tissue, without ceremony, without any external cause. It travels about a millimeter, sometimes a little less. The surrounding matter slows it almost immediately, and within that tiny distance, shorter than the width of a fingernail, it meets an electron, and the two dissolve into light. Two gamma rays, moving in opposite directions. Gone. The whole event takes place in a space you could not see without a microscope, in a time too short to name in ordinary language. And then it is over, and the body continues, unaware. This is not a dramatic process. It leaves no trace you would ever notice. It produces no sensation, no warmth, no signal of any kind that reaches your conscious mind. It simply happens, as so many things in the body happen, below the threshold of awareness, in the quiet machinery of matter. And it has been happening since long before anyone knew what a positron was. The positron was identified in 1932. The antiproton came later. Much later, in the scale of these things, it took until 1955 for physicists to produce an antiproton artificially for the first time. The machine that made it possible was called the Bevatron, a particle accelerator built in Berkeley, California. It was, at the time, one of the most powerful accelerators in the world, designed specifically to reach the energies needed to create proton-antiproton pairs. And it worked. The antiproton emerged from those collisions carrying the same mass as the proton, exactly the same, as far as any measurement could determine. But where the proton carries a positive electric charge, the antiproton carries a negative one. Same mass, opposite charge, mirror image, in that one precise sense. It was the confirmation of something that had been expected but not yet seen. The electron had its positron. Now the proton had its antiproton. The symmetry was deepening. And it continued to deepen. Not long after, the antineutron was found as well, which, at first, might seem like a strange thing to celebrate. A neutron carries no electric charge, so an antineutron also carries no electric charge. In that sense, they appear identical, and yet they are not. The difference lies deeper than charge. Both the neutron and the antineutron are composed of smaller particles called quarks. The neutron contains quarks of one type. The antineutron contains their antimatter counterparts, antiquarks. The charge cancels out in both cases, leaving zero, but the internal composition is opposite, and that difference is real and measurable, and it matters, because when a neutron meets an antineutron, they annihilate just as completely as any other particle meeting its antiparticle. The absence of charge does not mean the absence of an antimatter twin. It means the twin is hidden one layer deeper. This pattern, every particle paired with an opposite, is not a coincidence. It is a structural feature of the mathematics that describes how matter behaves at the smallest scales. The framework physicists use is called the Standard Model. It is, in a sense, the most carefully tested theory in the history of science. Its predictions have been confirmed by experiment after experiment to extraordinary precision. And one of its deep features, not an assumption, but a consequence of the mathematics, is that for every fundamental particle, there must exist a corresponding antiparticle. Same mass, opposite charge, and opposite values of certain other quantum properties. Every quark has an antiquark. Every lepton has an antilepton. The electron, the muon, the tau particle, The three types of neutrino. Each has a mirror counterpart. The six quarks: up, down, strange, charm, bottom, top. Each has an antiquark twin. There are exceptions, of a kind. Some neutral particles are their own antiparticles. The photon, for instance, the particle of light, is identical to its own antimatter version. There is no antiphoton distinct from the photon itself. The same is true of certain other neutral bosons, but these are special cases, and they are understood. For the vast majority of particles, the pairing is exact. And this means that when the universe began, when energy first condensed into matter, it should have produced equal amounts of both. For every particle, an antiparticle. For every proton, an antiproton. For every electron, a positron, in perfect balance, or very nearly so. And if the balance had been perfect, everything would have annihilated. Every particle would have found its partner. Every gram of matter would have met a gram of antimatter, and the universe would have dissolved entirely into light, a vast, featureless sea of photons, expanding and cooling, with nothing left to form stars or planets or anything at all. No structure, no chemistry, no time in any meaningful sense, because there would be nothing to mark its passage, just light, spreading outward through an empty universe. And yet, here we are. The universe did not annihilate itself. Something was not balanced. Something, in the first fraction of a second, was slightly asymmetric. For reasons that physicists have been working to understand for decades, matter was produced in just slightly greater quantities than antimatter. Not by much, roughly one extra matter particle for every billion matter-antimatter pairs. A margin so small it is difficult to hold in the mind. A billion particles annihilated, and one was left over. A billion more annihilated, and one more survived. And so on, across the entire early universe, in every direction, at every point in space. The annihilation was almost total. Almost. That remainder, that 1 in a billion surplus, is everything. Every star in every galaxy, every grain of dust drifting between them, every planet, every ocean, every living thing, every atom in your body, lying still right now in the dark. All of it is the remnant of that asymmetry. All of it is what was left after the annihilation was as complete as it could be. We exist because the balance was not quite perfect. Why it was not perfect is one of the deepest open questions in physics. A physicist named Andrei Sakharov identified, in 1967, 3 conditions that would need to be true for matter to come to dominate antimatter in the early universe. The conditions are precise, and they are all, in principle, testable. And physicists have found evidence that nature satisfies all 3 of them, at least partially, but only partially. The amount of asymmetry that has been measured in the behavior of certain particles, in the subtle differences between how matter and antimatter decay, is real. It is confirmed, but it is far too small to account for the surplus we observe. The mathematics does not close. Something is missing. Some source of asymmetry that the standard model does not yet contain. Some process, or some particle, or some interaction that has not yet been found. Physicists are looking. Carefully, patiently, with instruments of extraordinary sensitivity. But the answer is not yet in hand. And so the question remains open, quietly, at the foundation of everything. Why did matter survive? Why was the balance not perfect? Why is there something rather than the light of a universe that canceled itself out before it had the chance to begin? No one knows. Not yet. And that is all right. Some questions are large enough to hold for a while, to rest with rather than resolve, to let settle into the background, like the faint glow of the cosmic microwave background itself, present everywhere, ancient, patient. Still here, there is a quietness to certain particles. A photon, a single particle of light, has no antimatter twin. It is its own antiparticle. If a photon were to meet another photon, there would be no annihilation, no cancellation. They simply pass, or interact, or continue on their way. The photon carries no charge, no quality that could be reversed into an opposite. It is, in a sense, already balanced within itself. This is not true of most particles. Most particles carry something, charge, or a property called baryon number, or some other quantity that distinguishes them from their mirror image. And for those particles, the mirror image exists. Somewhere, in principle, there is an opposite. But the photon reminds us that the universe is not entirely divided into pairs. Some things simply are what they are, with no counterpart waiting on the other side. And yet, the fact that most particles do have counterparts, that most matter has a corresponding antimatter, leads to one of the deepest questions in all of physics. Why is there anything at all? Not in the philosophical sense, though that question is also worth holding, but in a very specific, physical sense. If the Big Bang produced matter and antimatter in nearly equal amounts, if every particle came paired with its opposite, then why did they not simply cancel? Why did the universe not annihilate itself in those first moments, leaving nothing behind but light? The answer, as far as we can tell, is that the balance was not quite perfect. For every billion matter-antimatter pairs that found each other and vanished, there was one extra matter particle left over. Just one, out of a billion. That remainder, that tiny, improbable surplus, is everything. Every star, every planet, every grain of dust drifting through the dark between galaxies, every atom that has ever formed anything. All of it descended from that fraction. Physicists have a name for the question this raises. They call it the baryon asymmetry problem. Baryons are a family of particles that includes protons and neutrons, the building blocks of atomic nuclei. The asymmetry is the imbalance between baryons and their antimatter counterparts. The problem is explaining where that imbalance came from. Because the laws of physics, as we understand them, do not obviously allow for it. If you wrote down the equations that govern particle interactions and ran them forward from a perfectly symmetric beginning, you would expect a perfectly symmetric result. Matter and antimatter in equal measure, and then nothing, as they canceled each other out. Something must have broken the symmetry. Something must have tilted the balance, even slightly, in favor of matter. In 1967, a Soviet physicist named Andrei Sakharov sat with this problem and identified what he believed were the three conditions necessary for matter to come to dominate antimatter. Three things that must have been true of the early universe for the surplus to have arisen. He was working largely in isolation at the time, in circumstances that were not easy, and yet the clarity of what he wrote has held for more than half a century. Three conditions, each one precise, each one pointing towards something the universe had to do, or be, in order for anything to exist. The first condition is this: baryon number must not be perfectly conserved. Baryon number is, in essence, a count of matter particles minus antimatter particles. In ordinary physics, this number is treated as fixed. It does not change. A proton does not simply become something with a different baryon number without a corresponding change elsewhere. But if baryon number were perfectly conserved, always, without exception, then the universe could never have developed a surplus. You cannot go from 0 to 1 if the rules forbid the count from changing. So Sakharov's first condition says, the rules must not be absolute. There must be some process, some interaction in which baryon number shifts, even rarely, even slightly. Whether such processes exist is still being investigated. They are predicted by certain theories, but they have not yet been directly observed. The second condition is quieter in its phrasing, but vast in its implications. The laws of physics must treat matter and antimatter differently. This property has a name, CP violation. CP stands for charge parity. Charge refers to the electrical charge of a particle. Parity refers to a kind of spatial mirror reflection. Flipping left and right, CP symmetry would mean that if you reversed both, if you replaced every particle with its antiparticle and mirrored the geometry of the interaction, the physics would look identical. But it does not, always. In certain rare decays, certain subtle interactions, matter and antimatter behave in ways that are not quite mirror images of each other. The difference is small. It has been measured, confirmed, studied carefully. It is real. But it is not large enough. The CP violation that has been found in laboratories, in the decay of particles called kaons, in the behavior of particles called B mesons, is genuine, but it falls far short of what would be needed to explain the surplus we observe. The mathematics, as has been said, does not close. Something more is needed, some additional source of asymmetry that has not yet been found. And so the second condition is met, in part, but only in part. The third condition is perhaps the most intuitive, once it is stated. The early universe must have passed through a period of thermodynamic imbalance. In a system that is perfectly in equilibrium, where every process is balanced by its reverse, where nothing is out of place, no net change can accumulate. If the universe had always been in perfect thermal balance, any asymmetry that arose would have been immediately undone. The surplus would have been erased as quickly as it formed. For the imbalance to stick, the universe had to move through a state of disequilibrium, a moment, or a transition, where things were not balanced, where the forward direction of time had a different character than the reverse, where the arrow of time, in some sense, was already present. The very early universe was expanding, cooling, changing phase. It was not in equilibrium. It was passing through transitions, like water becoming ice, but at energies and temperatures almost impossible to imagine. And in those transitions, in that disequilibrium, there was the possibility for asymmetry to take hold and remain. Sakharov's three conditions, taken together, form a kind of map. Not a solution, but a description of the terrain. They tell us what must have been true. They do not yet tell us exactly how it happened. The standard model of particle physics, the most precisely tested framework in the history of science, satisfies all three of them, at least partially, but only partially. The amount of asymmetry that has been measured, in the behavior of certain particles, in the subtle differences between how matter and antimatter decay, is real. It is confirmed, but it is far too small to account for the surplus we observe. The mathematics does not close. Something is missing. Some source of asymmetry that the standard model does not yet contain. Some process, or some particle, or some interaction that has not yet been found. Physicists are looking carefully, patiently, with instruments of extraordinary sensitivity. But the answer is not yet in hand. And so the question remains open, quietly, at the foundation of everything. Why did matter survive? Why was the balance not perfect? Why is there something, rather than the light of a universe that canceled itself out before it had the chance to begin? No one knows. Not yet. And that is all right. Some questions are large enough to hold for a while, to rest with, rather than resolve. To let settle into the background, like the faint glow of the cosmic microwave background itself, present everywhere, ancient, patient, still here. There is a word for the imbalance. A single word that physicists use to name the moment when the universe chose a side. CP violation. It sounds technical, and it is. But the idea beneath it is almost poetic in its simplicity. Imagine a process, a particle decaying, breaking apart into smaller pieces. Now imagine running that same process in a kind of mirror, not just a reflection of space, but a deeper mirror, one that also swaps every particle for its antiparticle, every positive charge for a negative one. If the laws of physics were perfectly symmetric, the mirrored process would look identical. The same rates, the same outcomes, the same behavior. But sometimes, they don't. Sometimes the mirror version runs just slightly differently. The decay happens at a slightly different rate. The products emerge in slightly different proportions. Matter and antimatter, it turns out, do not always behave as perfect reflections of each other. That difference, that subtle, stubborn asymmetry, is what physicists call CP violation. C stands for charge. P stands for parity, which is a way of describing spatial orientation, the handedness of a process. When both are reversed simultaneously and the result still differs, the symmetry is broken. And the universe, it seems, has always known this. The first experimental evidence came in 1964, a quiet but consequential year in physics. Two researchers, James Cronin and Val Fitch, were studying the decay of particles called kaons. Kaons are strange particles, not strange in the colloquial sense, but strange in the technical one, containing a type of quark called the strange quark. They are unstable, short-lived, and they decay in ways that can be measured with great precision. What Cronin and Fitch found was that kaons did not decay symmetrically. Matter kaons and antimatter kaons behaved slightly differently from each other. The difference was small, almost imperceptibly small. But it was there, and it was real, and it could not be explained away. CP symmetry, which many physicists had assumed was inviolable, was violated. The discovery earned Cronin and Fitch the Nobel Prize in Physics in 1980, and it opened a door that has not fully closed since. In the decades that followed, physicists found CP violation in other particles as well. Particles called B mesons, heavier, more complex, containing a bottom quark, showed CP violation that was larger and somewhat easier to study. Dedicated experiments were built to measure it. The Babar experiment in California, the Bell experiment in Japan, both confirmed that CP violation was real, that it followed the patterns the Standard Model predicted, and that it was present in the universe at a measurable level. And yet, the measurements confirmed the theory. And the theory was not enough. The amount of CP violation observed in kaon decays, in B meson decays, in every system that has been carefully examined, it is genuine, it is not in dispute. But when physicists calculate how much matter surplus that asymmetry could have produced in the early universe, the number falls short, far short, by many orders of magnitude. The observed universe contains roughly one extra matter particle for every billion matter-antimatter pairs that annihilated. That is, the surplus that needs to be explained. And the CP violation measured in the Standard Model accounts for only a tiny fraction of it. The mathematics, as it stands, does not produce a universe like this one. Something is missing. This is not a failure of the experiments. The measurements are among the most precise in all of science. This is a gap in the theory itself, a signal that the standard model, for all its extraordinary power, is incomplete in this particular way. The standard model is worth pausing on for a moment. It is the framework that describes all known fundamental particles and 3 of the 4 fundamental forces. It has been tested to a degree of precision that is almost difficult to hold in the mind. Some of its predictions have been confirmed to more than 10 decimal places. It predicted the existence of particles before they were found, described interactions before they were measured, and has not been meaningfully contradicted by experiment in decades. It is, by any reasonable measure, the most precisely tested theory in the history of science. And yet, it cannot explain why you exist. Not fully, not in this particular way. The matter-antimatter asymmetry, the reason the universe contains structure rather than light, lies just beyond what the standard model can account for. The theory is not wrong, but it is not complete. There is something it does not yet see. Physicists believe there must be additional sources of CP violation, processes, or particles or interactions that have not yet been discovered. Sources of asymmetry that operated in the early universe and left their mark on everything that followed, but that have not yet revealed themselves in any laboratory. The search for them is ongoing, careful, methodical, patient. And woven through all of this is a single word that names the process itself: baryogenesis. It is the name physicists give to whatever happened in the early universe to generate the matter-antimatter asymmetry. Baryon is the category of particle that includes protons and neutrons, the building blocks of atomic nuclei, the substance of stars and planets and living things. Genesis, in the oldest sense of the word, simply means origin. Baryogenesis is the origin of matter. The precise mechanism is not known. There are candidates, there are theories, there are frameworks that satisfy Sakharov's conditions in various ways, but no single model has been confirmed. No experiment has yet pointed clearly to the process that tipped the balance. What is known is that it happened. It must have happened. The evidence is everywhere, in every atom, in every galaxy, in the simple fact that the universe did not annihilate itself in its first moments. Something broke the symmetry. Something, in the first fractions of a second, gave matter a slight and permanent advantage. And from that advantage, from that margin of 1 in a billion, everything followed. The stars, the dust between them, the slow accretion of matter into worlds, the long, patient chemistry of carbon and water and time. All of it rests on a process that is not yet fully understood, a moment so early and so brief that no instrument has yet reached it directly, a symmetry breaking that left no clear record, only its consequence, which is everything. There is something quietly humbling in that. The most tested theory in science points toward its own incompleteness. The most fundamental question about matter's existence remains, at its core, unanswered, and the universe continues, indifferent to the gap, filled with the remnants of an asymmetry it generated and then moved on from. Baryogenesis happened once, in the first instant, and then the universe cooled and the pairs annihilated, and the survivors were left in the silence that followed. And the silence became space, and space became time, and time became this. Whatever this is, this long, slow expansion, this scattering of light across distances that have no comfortable name, it began with a number. 1. One extra particle for every billion that canceled. That is the margin. That is the inheritance. Rest in it for a moment. The question does not need to be resolved tonight. It has waited since the beginning of everything. It can wait a little longer. There is another thread worth following quietly. One that does not begin with quarks, but with something lighter. Leptons. The family of particles that includes electrons and the far more elusive neutrinos. Some physicists believe the asymmetry did not begin with matter in the way we usually picture it. They suggest it began earlier, or differently, with an imbalance among leptons, which then transferred through processes in the hot early universe into the matter surplus we observe today. This idea is called leptogenesis. It is not a settled theory. It is a possibility, carefully constructed, that fits within what we know without contradicting it. The thought is this, that in the very early universe, heavy relatives of the neutrino may have decayed in a way that slightly favored one side over the other, and that preference, small as it was, eventually became the world. The neutrino sits at the center of this, and the neutrino is, in many ways, the most difficult thing in physics to know. It has almost no mass. It carries no electric charge. It passes through matter as though matter were not there. Billions of neutrinos are moving through your body right now, in this quiet room, in this quiet moment. They will not stop. They will not slow. They will continue through the floor, through the earth, out the other side, and into the dark between galaxies without ever noticing that anything was in their way. This makes them extraordinarily hard to study. And that difficulty matters because neutrinos may be hiding something. They may violate CP symmetry, that property which requires the laws of physics to treat matter and antimatter equally in ways that have not yet been measured. The experiments capable of testing this are running now, or being built, but the answer is not yet in hand. The neutrino keeps its secrets with a patience that feels almost geological. So the question of where the asymmetry began remains open at both ends. It may have started with quarks through baryogenesis. It may have started with leptons through leptogenesis. It may have involved both in ways that are still being untangled. What is not in question is the asymmetry itself. Roughly one extra matter particle for every billion pairs. That number is worth sitting with again, not because it is dramatic, but because it is so precise in its consequence. 1 in a billion, not 1 in 100, not 1 in a trillion. The universe arrived at a ratio in its first moments that permitted everything that followed. And the margins on either side of that ratio are narrower than they might seem. If the asymmetry had been smaller, if the imbalance had been even slightly less pronounced, the annihilation would have been more complete. The matter and antimatter would have canceled more thoroughly. What remained would not have been enough to form atoms, or clouds of gas, or the slow gravitational gathering that eventually becomes a star. The universe would have become a vast, featureless sea of light. Photons moving through expanding space, with nothing to illuminate, nothing to warm, nothing to pull together into any kind of structure. No galaxies, no dust, no time, in any sense that a living thing could experience. Just light, spreading outward, growing colder, growing thinner, until even the light was too diffuse to mean anything. That is what a slightly smaller asymmetry would have left behind. And on the other side of that number, if the asymmetry had been larger, the universe would also have been different, though in ways that are harder to state simply. More matter surviving means more material to work with. But the relationships between density and expansion, between gravity and the rate at which the universe cooled, are delicate. A larger asymmetry might have produced a universe that collapsed back on itself too quickly. or one that formed structure in ways that left no room for the slow, patient chemistry that eventually produces something capable of asking questions. The precise consequences are still being studied. Physicists are careful here because the interactions between these variables are complex, and certainty would be premature. What can be said is that the number the universe chose, 1 in a billion, sits in a region that permitted complexity. Whether that is remarkable or simply the only version of events we could ever find ourselves inside is a question that touches the edges of physics and does not resolve cleanly. It is enough, for now, to notice the number and to let it rest there without forcing it to mean more than it does. Somewhere in Geneva, in a laboratory built into the Earth, a different kind of patience is being practiced. The Alpha experiment at CERN has been doing something that would have seemed almost impossible not long ago. It has been making antihydrogen and holding it. Antihydrogen is the simplest imaginable antimatter atom, a single antiproton, the antimatter twin of the proton, carrying a negative charge where the proton carries positive, orbited by a single positron, the antimatter twin of the electron. Together, they form a structure that mirrors hydrogen in every way that can currently be measured. To make antihydrogen, the experimenters must first produce antiprotons, slow them down, cool them, and bring them together with positrons in a carefully controlled space. The antiprotons come from a particle accelerator. The positrons come from a radioactive source. Bringing them together without losing them to annihilation requires magnetic fields shaped with extraordinary precision. And then, if everything holds, an antiproton and a positron find each other and settle into orbit. An antimatter atom, existing in the middle of a world made entirely of matter. The container cannot touch it. Any contact with ordinary matter ends the atom instantly, converting it entirely into energy. So the antihydrogen floats, suspended in magnetic fields, held away from the walls of its own trap by forces carefully tuned to keep it in place. For a long time, antihydrogen could only be held for fractions of a second. The early experiments at CERN in 1995 produced antihydrogen atoms that survived for nanoseconds before finding the walls and vanishing, each one a brief existence, measured in billionths of a second before annihilation. But the experiments grew more refined. By 2011, Alpha had extended that time to over 1,000 seconds, long enough to begin asking the antihydrogen questions, long enough to shine light on it and listen for what it said back. The number of atoms held at any one time is measured in the hundreds, not grams, not milligrams, hundreds of individual atoms, each one a small, fragile thing suspended in a magnetic field in a room underground. It is, in its way, one of the quieter achievements of physics. Not loud, not fast, not visible to the eye. Just a handful of antimatter atoms, drifting in a trap, waiting to be understood. And what they are beginning to reveal is something the universe has been keeping to itself for a very long time. Whether antimatter, when examined closely enough, is truly the mirror of matter, or whether some small difference lies waiting in the measurements, patient as the neutrino, quiet as the asymmetry itself. The answer is not yet complete, but the asking has begun. And that, for now, is enough. One of the first things physicists wanted to ask antihydrogen was a simple question. Does it fall? Not a complicated question on its surface. Every object you have ever held, every leaf that has drifted from a tree, every breath that has settled back down after rising, all of it falls. Gravity pulls, and things respond. That is so ordinary, so woven into the texture of life, that it barely registers as a fact at all. And yet for decades, no one knew whether antimatter did the same. The question had been open since the first antiparticles were found. Since Dirac's equations implied a mirror world, physicists had wondered whether that mirror extended to gravity itself, whether an antiproton, released in a vacuum, would drift downward like its ordinary twin, or whether something in its nature might cause it to behave differently. Some theories, now largely disfavored but never fully closed, suggested antimatter might fall upward, that gravity, for antimatter, might be repulsive rather than attractive. It sounds like the kind of question that should be easy to answer. It was not. To test how antimatter responds to gravity, you first need antimatter that stays still long enough to be watched. And for most of the history of the field, that was the obstacle. Antiparticles moved too fast, annihilated too quickly, vanished before any measurement of their gravitational behavior was possible. The first antihydrogen atoms created at CERN in 1995 existed for nanoseconds, fractions of a breath. They formed, drifted, touched the walls of the apparatus, and were gone. There was no time to ask them anything, no time to watch them fall or float or do anything at all except disappear. The years that followed were years of refinement, of learning how to slow antiparticles down, how to coax them into combining, how to hold the resulting atoms away from every surface that would destroy them. Magnetic fields, shaped with great care, could push against the tiny magnetic moment of the antihydrogen atom and keep it suspended in the center of a trap, not touching anything, not annihilating, just existing, briefly, in a kind of enforced stillness. By 2011, that stillness had been extended to over 1,000 seconds. And with that time came the possibility of measurement. The gravity experiment came later still. It required not just trapping antihydrogen, but trapping enough of it, consistently enough, to watch what happened when the magnetic fields were gently relaxed and the atoms were allowed to drift freely. To see, in the pattern of where they annihilated against the trap walls, whether they had moved upward or downward in the moments before contact. The answer, confirmed by CERN in 2023, was quiet and in some ways expected. Antihydrogen falls downward. It responds to gravity the way ordinary matter does, at least within the precision of that measurement. The universe, in this respect, does not appear to distinguish. Antimatter is not repelled by the Earth. It does not drift toward the ceiling. It falls, as everything falls, toward the center of mass below it. For some, this was a small disappointment, not because the result was unwelcome, but because the difference would have been extraordinary. A crack in the symmetry large enough to see, but physics is not always rewarded with the dramatic answer. Sometimes the universe simply confirms what the equations suggested, and the work continues. And the work does continue, because gravity is only one question. The other question, older, in some ways more fundamental, is about light. Every element, when excited, emits light at specific frequencies. Precise, characteristic, like a fingerprint. Hydrogen, the simplest atom, has one of the most studied spectra in all of science. Its lines have been measured to extraordinary precision over more than a century. The Lyman series, the Balmer series, patterns of color and wavelength that encode the structure of the atom itself, the energy levels of the electron as it moves between states. If antihydrogen is truly the mirror of hydrogen, its spectrum should be identical. The same frequencies, the same fingerprint, because the antiproton and the positron, bound together, should obey the same quantum mechanical rules as their ordinary counterparts, the same equations, the same energy levels, the same light. And so far, within the precision of current measurements, that appears to be true. The spectral lines of antihydrogen match those of hydrogen. The light it emits, when probed with lasers in the underground trap at CERN, falls at the frequencies the equations predict. No deviation has been found. But the measurements are not yet precise enough to be certain. Hydrogen's spectrum has been measured to more than 15 significant figures in some transitions. Antihydrogen's measurements are still far less precise, limited by the small number of atoms available and the difficulty of holding them long enough to probe carefully. The comparison is real, but it is not yet a fair one. There is still room in the gap between what has been measured and what could, in principle, be measured, for a small difference to be hiding. And a small difference would matter enormously if the spectrum of antihydrogen were found to differ from hydrogen's, even slightly, even at the 14th decimal place. It would mean that the laws of nature are not the same for matter and antimatter at the most fundamental level. It would be a violation of something called CPT symmetry, the principle that the combined reversal of charge, parity, and time must leave the laws of physics unchanged. CPT symmetry is not just a guess, it is a theorem derived from the deepest foundations of quantum field theory. It is considered one of the most robust predictions in all of physics. No experiment has ever found a violation of it. But no theorem is beyond testing. And antihydrogen, drifting in its magnetic trap beneath the hills near Geneva, is one of the most precise tests ever attempted. Each measurement is a question asked of the universe in very careful language. Each result that matches the prediction is a confirmation, not a proof, but a confirmation that the mirror holds that matter and antimatter, whatever their differences in abundance, obey the same underlying rules. And each refinement of the measurement is a step closer to the place where a difference, if one exists, might finally become visible. This is slow work. It is the kind of work that does not announce itself. No single experiment resolves the question. No single morning brings the answer. It accumulates, the way understanding always accumulates, in small increments, in careful repetitions, in the gradual narrowing of uncertainty. Hundreds of atoms, held for minutes at a time, probed with light, watched as they fall. It is not the scale of the question that makes the work feel small. The question is, as large as the universe itself. Why does anything exist? Why did matter survive? What is the nature of the mirror that separates what is from what was annihilated? It is simply that the answers, when they come quietly. A spectral line that matches a falling atom that falls the right way, a measurement that agrees with the one before it and the one before that. And somewhere in the accumulation of those quiet agreements, or perhaps in the first quiet disagreement, when it finally arrives, the universe may begin to say something it has not said before. Something about why it kept the matter. Something about why it kept us. There is a theorem that sits beneath all of this. A quiet mathematical law that physicists call CPT symmetry. It does not describe one thing, or two things, but three things held together: charge, parity, and time. And it says that if you reverse all three at once, the laws of physics must look exactly the same. This is not an assumption. It is a consequence. Something that falls out of quantum field theory the way a shadow falls from a shape. Any consistent description of particles and forces, written in the language of that theory, must obey it. There is no known way to construct a coherent physics without it. And from that theorem, something very specific follows. A particle and its antiparticle must have exactly equal mass. Not approximately equal. Not equal within the limits of our instruments. Equal. The same number. Precisely. to whatever decimal place you care to measure. They must also carry charges that are equal in size and opposite in sign. The electron carries a charge of -1. The positron carries a charge of +1, not positive 1.001, positive 1. The same magnitude, mirrored. This is what CPT symmetry requires. And so far, every measurement ever made has confirmed it. The proton and the antiproton, weighed against each other with extraordinary care, agreed to better than 1 part in 10 billion. The electron and the positron, compared across decades of experiment, show no difference in mass that any instrument has yet been able to detect. The agreement is almost unsettling in its precision. Because if there were a difference, even a very small one, it would mean that CPT symmetry is broken, and that would mean that the foundation beneath quantum field theory has a crack in it, a place where the mathematics, however beautiful, does not quite describe the world. It would be among the most significant discoveries in the history of physics. Not because it would answer the matter-antimatter question directly, but because it would mean the universe is even stranger than the standard model suggests, that the mirror between matter and antimatter is not just tilted, as CP violation shows, but warped in some deeper way that no current theory anticipates. Physicists search for that crack carefully. They weigh antiparticles against particles with the most sensitive instruments they can build. They compare spectral lines, measure magnetic moments, look for any number that does not quite match its mirror image. And so far, the mirror holds. But the search continues, because the universe has already shown, in the matter-antimatter asymmetry itself, that something broke the symmetry once, and a symmetry that broke once may have left other traces, in places not yet examined with sufficient care. So the measurements go on, quiet, patient, precise. And while the laboratories work in their careful stillness, the sky above is doing something else entirely. Every moment, from every direction, particles are falling through space toward the Earth. Cosmic rays, protons, and heavier nuclei, accelerated by distant supernovae and other violent processes across the galaxy, arrive at the top of the atmosphere traveling at nearly the speed of light. When they strike the thin air of the upper atmosphere, they do not pass through quietly. They collide with the nuclei of oxygen and nitrogen atoms, and those collisions produce cascades, showers of secondary particles that multiply downward through the atmosphere, like ripples spreading from a stone dropped in still water. Among those secondary particles are positrons, antimatter, falling from the sky, not from a laboratory, not from a machine, but from the ordinary violence of the cosmos, produced in the upper air and detectable, with the right instruments, at ground level. The atmosphere is, in this sense, a kind of natural accelerator, one that has been running continuously for as long as the Earth has had an atmosphere, producing antimatter quietly, constantly, in the thin, cold air above the clouds. And the Earth is not the only place where this happens. High above the plane of the Milky Way, a telescope drifts in orbit, the Fermi Gamma Ray Space Telescope, watching the sky not in visible light, but in gamma rays, the most energetic form of electromagnetic radiation, the same kind produced when matter and antimatter annihilate. And Fermi has seen something rising from the center of the galaxy, a glow of gamma rays at a very specific energy, 511,000 electron volts, the precise energy signature of positron annihilation, an electron and a positron, meeting somewhere near the galactic center, converting entirely into 2 gamma-ray photons, each carrying exactly that energy. The signal is not faint. It is one of the brightest features in the gamma-ray sky, a steady, diffuse glow concentrated toward the center of the Milky Way. spreading outward in a roughly spherical shape. Something near the heart of our galaxy is producing positrons in enormous quantities. And the source is not fully understood. There are candidates, pulsars, which are rapidly spinning neutron stars, can produce positrons in the intense electromagnetic fields near their surfaces. Supernovae leave behind radioactive isotopes that decay and emit positrons as they cool. The region near the galactic center is crowded with old stars, with stellar remnants, with processes that could, in principle, account for some of what Fermi sees. But the numbers are difficult to reconcile. The rate of positron production implied by the signal is higher than the known sources seem able to explain. And the spatial distribution, the way the glow spreads, does not match perfectly with any single proposed source. So the question remains open. Some physicists have suggested something quieter and stranger, that the positrons at the galactic center might not come from stars at all, that they might come from dark matter. Dark matter, whatever it is, fills the galaxy in a halo that is densest toward the center. If dark matter particles can annihilate with each other, if they are, in some sense, their own antiparticles, then the galactic center is exactly where that annihilation would be most frequent. And if that annihilation produces positrons as a byproduct, the signal Fermi sees might be a faint echo of dark matter destroying itself in the crowded heart of the Milky Way. It is a possibility, not a conclusion. The data are consistent with it, but consistent with other explanations too. This is the nature of the galactic center. It is so dense with activity, so layered with overlapping processes, that separating one signal from another requires a patience that matches the scale of the question. The measurement continues. New instruments, new analyses, new attempts to separate the contributions of pulsars and supernovae and whatever else might be there from the possibility of something that has never been directly observed. And so the antimatter story, which began in a cloud chamber in 1932, with a single particle curving the wrong way, has grown to fill the sky. It is in the hospitals where positrons image the living body from within. It is in the upper atmosphere where cosmic rays produce it silently above the clouds. It is in the traps at CERN, where a few hundred antihydrogen atoms are held in magnetic suspension and measured with extraordinary care. It is in the gamma-ray glow at the center of the galaxy, rising from a source that has not yet been named with certainty. And it is in the question that underlies all of it, the question that the universe has not yet answered, the question written into the fact that anything exists at all. Why matter? Why this one part in a billion that was not canceled? Why the remnant? The answer, if it comes, will come the way all answers in this field come. Not in a single moment, not in a single experiment, but in the slow accumulation of measurements that agree, and then, one day, in the measurement that does not. Until then, the glow at the center of the galaxy continues. The positrons fall through the atmosphere. The antihydrogen atoms are held, and probed, and released. And the universe keeps its reason to itself, for now. One of the theories about that galactic glow involves something even less understood than antimatter itself. Dark matter, the unseen substance that makes up most of the mass in the universe, may not be entirely passive. Some models suggest that dark matter particles, whatever they are, could be their own antiparticles. And if two of them met, they would annihilate. Just as a particle and its antiparticle vanish into energy, two dark matter particles colliding in the dense center of the galaxy might produce a cascade of secondary particles, including positrons. The math, in certain models, works out. The galactic center is crowded with dark matter, according to our best estimates of how it clusters. It is exactly the kind of place where such annihilations, if they happen at all, would happen most often. And the positron signal that the Fermi telescope sees rising from that region, it is not obviously inconsistent with that picture. But it is not confirmed either. There are other explanations: pulsars, stellar remnants, processes that do not require dark matter at all. The signal exists. The source remains open. And so the glow at the center of the galaxy sits at the intersection of two of the deepest mysteries in physics: the origin of the matter-antimatter asymmetry and the nature of dark matter itself. Two unknowns, possibly touching, possibly illuminating each other, or possibly entirely unrelated. That uncertainty is not a failure of science. It is where science lives, most of the time. There is a practical side to all of this, quieter than the cosmology, but no less strange. If you wanted to hold antimatter, to keep it, to study it, to prevent it from vanishing the moment it was made, you would face a problem with no ordinary solution. You cannot put antimatter in a box. Not a glass box, not a metal box, not a ceramic box. Any material surface is made of matter, and the moment an antiparticle touches that surface, it meets a matter particle, and both of them are gone. The annihilation is not violent in the way an explosion is violent. It is simply immediate. A positron drifting toward a glass wall does not slow down and stop. It touches the first electron it encounters, and both become gamma rays in an instant so brief it has no perceptible duration. The container does not hold the antimatter. The container destroys it. The solution that physicists found is to use no container at all, not in the ordinary sense. Instead, they use fields, magnetic fields and electric fields, shaped with great precision, can exert forces on charged particles without touching them. A charged antiparticle suspended in a carefully arranged magnetic field floats in the center of that field, held away from every surface by invisible pressure. It never touches the walls. Because in a sense, there are no walls, only forces, curving inward from all directions, keeping the particle exactly where it is. This is called a trap. And building one that works for antihydrogen, which is electrically neutral overall, and therefore harder to hold with electric fields alone, required decades of engineering and a great deal of patience. Antihydrogen has a tiny magnetic moment, a faint response to magnetic fields that comes from the spin of its constituent particles. That faint response is enough. A magnetic trap shaped just so can hold a neutral antihydrogen atom suspended in vacuum, away from every surface, for as long as the fields are maintained. The vacuum itself must be extraordinarily pure. Even a few stray molecules of ordinary gas drifting through the trap would collide with the antihydrogen and end it. The pressure inside the trapping region at CERN's Alpha experiment is lower than the pressure of interstellar space, lower than almost anywhere else on Earth. And still, the trapping is fragile. A small fluctuation in the magnetic field, a vibration in the apparatus, a single unwanted particle, and the antihydrogen is gone. When everything works, when the fields hold steady and the vacuum holds clean, and the antihydrogen atoms are guided into the trap one by one, the number that can be held at any given moment is not large. Not large at all. The record, as of recent years, is measured in the hundreds. A few hundred antihydrogen atoms suspended in a magnetic field in a room temperature laboratory on a planet made entirely of matter. That is the largest quantity of antihydrogen ever held at one time. hundreds of atoms. To put that in some kind of scale, a single grain of table salt contains roughly 10 million billion atoms. The entire inventory of trapped antihydrogen in human history would not be visible to the naked eye. It would not be visible to any ordinary instrument. It exists only because the detectors surrounding the trap can register the gamma rays that appear when the antihydrogen is released and annihilates. That flash of annihilation radiation is the proof that it was there. And yet, from those few hundred atoms, held for minutes or hours at a time, physicists have measured the spectrum of antihydrogen. They have measured how it falls under gravity. They have begun to compare it, line by line, with the spectrum of ordinary hydrogen. The smallness of the sample has not prevented the measurement. It has only made the patience required to take it more extraordinary. The difficulty of trapping antimatter points towards something else, something that makes the idea of producing it in useful quantities feel very distant. Creating antimatter requires energy, a great deal of energy. When a particle accelerator produces an antiproton, it does so by accelerating a proton to enormous speed and slamming it into a target. The collision produces a spray of particles, and among them, occasionally, an antiproton. The process is inefficient in ways that are almost difficult to hold in mind. To produce a single gram of antiprotons, 1 gram, the weight of a small paperclip, with the technology that exists today, would require more energy than humanity currently generates across all its power sources over the course of several years. Not a day, not a month, years. And the cost, if you try to account for it in ordinary terms, has been estimated at tens of quadrillions of dollars. A quadrillion is 1,000,000 billion. Tens of them. For 1 gram. That number is not meant to be grasped precisely. It is meant to convey a distance, the distance between where we are and where we would need to be for antimatter to be anything other than a laboratory curiosity measured in atoms. There is a certain quietness in that distance. Antimatter propulsion, the idea of using matter-antimatter annihilation to drive a spacecraft, releasing energy with perfect efficiency, is not impossible in principle. The physics permits it. The energy density is real, but the gap between the physics and the engineering is so vast that it belongs, for now, to the same category as the questions about the galactic center and the baryon asymmetry. Something that is true in principle, something that the universe allows, but something that remains, for the moment, beyond the edge of what human hands can build. And perhaps that is fitting. Antimatter is, in a sense, the universe's most carefully guarded substance. It cannot be held by ordinary matter. It can only be held by the absence of matter, by fields, by vacuum, by the careful shaping of invisible forces. It exists in the world in the smallest possible quantities. And it carries, in those small quantities, the memory of a time when it was everywhere. When the universe was young enough that matter and antimatter were equals. Before the asymmetry, before the remnant, before any of this. So we rest here, for a moment, at the edge of what is possible. The physics is real. The energy is real. And yet the thing itself remains out of reach, not because the universe forbids it, but because the distance between understanding something and building something can be, in its own way, as vast as the distance between stars. And so we turn, gently, away from what might one day be, and back toward what was. Back toward the beginning. There was a time so early in the life of the universe that the word time itself barely applies, when the temperature of everything was beyond any scale we use today. Not hot the way a fire is hot, not hot the way the surface of a star is hot, but hot in a way that meant matter and energy were the same thing, continuously exchanging, continuously becoming one another. In those first fractions of a second, the universe was a kind of plasma, not the plasma of a lightning bolt or a fusion reactor, but something far more fundamental, a plasma of quarks and antiquarks, of electrons and positrons, of particles and their mirrors, all moving so fast, all packed so closely, that creation and destruction were happening everywhere at once. A particle would form and almost immediately meet its antiparticle, and both would vanish into light. And then, from that light, two new particles would form, and the cycle would begin again. This was thermal equilibrium. The universe was so energetic that it could continuously replenish what it destroyed. Matter and antimatter were not competing. They were simply two faces of the same restless energy, flickering in and out of existence at a rate too fast to follow. There was no surplus, yet no winner, just an endless, churning balance. And then the universe began to cool. It had been expanding since the very first moment, stretching outward in all directions, thinning, slowing, and as it expanded, it cooled. The way any gas cools when it is given more room. The way a breath of air cools as it spreads into a cold morning. And cooling changed everything. There is a threshold, a specific temperature, tied to the mass of a particle, below which the universe no longer has enough energy to spontaneously create a matter-antimatter pair from nothing. Below that threshold, pair production stops. The universe can no longer replenish what it loses. And so the annihilation continued, but the creation did not. Particle met antiparticle, and both disappeared, and nothing new came to replace them. The universe was consuming itself, and in that consumption, the asymmetry revealed itself. For every billion pairs that found each other and annihilated, there was one particle left over, one matter particle with no mirror to meet, one survivor in a universe that had just erased nearly everything. Those survivors were quarks. In the very earliest moments, before protons and neutrons existed, the fundamental building blocks of matter were quarks, the smaller constituents that would later combine. Quarks and their mirrors, antiquarks, had been annihilating throughout that first hot plasma. And when the annihilation was over, when the temperature had dropped far enough that the balance could no longer be maintained, what remained was a small excess of quarks. Alone, now, in a universe that had grown quiet enough to let them stay. And they did not stay alone for long. As the universe continued to cool, as the seconds passed, and we are still speaking of the first few minutes of all of time, those surviving quarks began to find one another. The strong nuclear force, which binds quarks together with extraordinary tenacity, drew them into combinations. 3 quarks bound together became a proton. 3 quarks of a different arrangement became a neutron. The building blocks of every atom that would ever exist were assembled in those first few minutes. From the remnant, from the 1 in a billion surplus, from the quarks that had no antiparticle left to meet. Everything. It is worth pausing here, in the stillness, to consider what made the asymmetry possible at all. Because the universe did not have to be this way. The laws of physics, as far as we can tell, are almost perfectly symmetric between matter and antimatter. Almost. There is one force, one of the 4 fundamental forces that govern all interactions in nature, that does not treat them equally. The weak nuclear force. The weak force is responsible for certain kinds of radioactive decay. It is the force that allows a neutron to transform into a proton, releasing an electron and a neutrino in the process. It operates at extraordinarily short ranges, far smaller than the nucleus of an atom. And it is, in most respects, a quiet and subtle force. But it has a quality that the other forces do not. The strong nuclear force, the one that binds quarks into protons and neutrons, treats matter and antimatter identically. As far as any experiment has been able to determine, electromagnetism, the force behind light and electric charge, does the same. Gravity, as the recent measurement of antihydrogen confirmed, appears to treat them equally as well. But the weak force does not. The weak force is the only known force that can distinguish between a particle and its antiparticle. That can, in a precise technical sense, tell the difference between matter and antimatter and behave differently toward each. This property, CP violation, the breaking of the symmetry between charge and spatial reflection, has been measured in the laboratory, in the decay of kaons and the decay of B mesons. It is real, and it is confirmed. And yet, the amount of CP violation that the weak force produces, as measured in those experiments, is not enough, not nearly enough to account for the surplus we observe, not enough to explain why one quark in a billion survived when all the others canceled out. The standard model of particle physics, the most precisely tested framework in the history of science, contains CP violation, but not enough of it, which means that somewhere in the physics we have not yet found, there is more asymmetry waiting to be discovered, more places where the universe treats matter and antimatter differently, more of the answer. We do not know where it is. We know it must exist, and that is where the story rests. For now, not at a conclusion, but at an open door. The universe cooled, the pairs annihilated, the quarks survived, the protons and neutrons formed, and from those first few minutes of extraordinary violence and extraordinary subtlety, everything that followed became possible. Every star that ever burned, every grain of dust drifting between galaxies, every atom in every molecule, in every living thing that has ever existed on this small, quiet world. All of it is the remnant. All of it is the 1 in a billion. All of it survived because the weak force, in some way we still do not fully understand, tilted the balance by the smallest possible amount at the earliest possible moment in a universe that was otherwise trying to erase itself. And here we are, resting in the quiet, made of survivors. The weak force carries the asymmetry, but the other forces, the strong nuclear force and electromagnetism, they do not. As far as every experiment has been able to determine, those two forces treat matter and antimatter in exactly the same way. A proton and an antiproton feel the pull of electromagnetism identically, only in opposite directions. The strong force, which binds quarks together inside protons and neutrons, binds antiquarks together inside antiprotons with equal strength, equal precision, no difference, none that has ever been measured. And so the asymmetry is not spread evenly across all of physics. It is concentrated, narrow, tucked inside the weak force, which governs certain kinds of decay, certain transformations of one particle into another. It is there, in that quiet corner of the standard model, that the universe keeps its secret, or part of it. Because the weak force alone, as we understand it, does not carry enough asymmetry to explain what we see. And so physicists have looked for other places where the difference might hide. One of those places is a family of particles called B mesons. A B meson is not a particle most people ever think about. It lives for less than a trillionth of a second before decaying into other things. It contains a bottom quark, one of the heavier, more unstable members of the quark family, bound together with another quark or antiquark, and in the way it decays. In the particular paths it takes as it falls apart, it shows CP violation. More of it than kaons show. Clearer, easier to measure, easier to study. When physicists realized this, they built machines specifically designed to produce B mesons by the millions, to watch them decay, to compare the behavior of B mesons with their antimatter counterparts, the anti-B mesons, and to measure, as precisely as possible, how differently the two behaved. Two experiments rose to that task in the early years of this century. One was called Babar, built at a laboratory in California. The other was called Bell, built in Japan. Both were what physicists call B factories, accelerators designed not for the highest possible energies, but for the highest possible production of one specific particle, tuned carefully to the mass of the B meson, running for years, accumulating data, watching decay after decay after decay, and they found it. CP violation in B meson decays, measured clearly, measured precisely, measured at the level the standard model had predicted. It was a confirmation of something deep, a verification that the theory was right about this particular asymmetry, in this particular particle, at this particular scale. And yet, the amount was not enough. The CP violation in B mesons, like the CP violation in kaons before them, is real and it is small. And when you calculate whether it could account for the matter surplus that fills the observable universe, the answer comes back the same way it always does. Not even close. The standard model's CP violation, in all the places it has been found, adds up to a fraction of what would be needed. The universe we live in, with its hundreds of billions of galaxies, each containing hundreds of billions of stars, required far more asymmetry than the known physics can provide. So the search continues. There are theories that reach beyond the standard model, extensions and elaborations that propose new particles, new forces, new symmetries that are broken in new ways. One of the most studied is called supersymmetry, a framework that pairs every known particle with a heavier partner particle, a shadow version that has not yet been observed. Supersymmetry, in many of its forms, predicts additional CP violating processes, new places where matter and antimatter would be treated differently, new contributions to the asymmetry that the standard model alone cannot provide. Those particles have not been found. The experiments that might have seen them have looked carefully, and the shadows have not appeared. Not yet. That does not mean they are not there. It means the search is ongoing, and the universe is not making it easy. And so the matter-antimatter asymmetry remains open. It sits alongside two other great unanswered questions in cosmology, three problems that define the edges of what we know, three places where the universe has declined, so far, to explain itself. The first is the asymmetry itself. Why matter survived, why antimatter did not, why the balance tipped by 1 part in a billion and left behind everything we see. The second is dark matter, the invisible substance that makes up most of the mass in the universe, that holds galaxies together, that shapes the large-scale structure of everything, and that has never been directly detected, never identified, never explained in terms of any particle the standard model contains. The third is dark energy, the still more mysterious presence that is causing the expansion of the universe to accelerate, pushing galaxies apart at an ever-increasing rate, working against gravity on the largest scales, and understood, at present, almost not at all. Three problems. three open doors. And they are not entirely separate. Some physicists suspect they are connected, that the same physics beyond the standard model that explains the matter surplus might also illuminate dark matter, that the universe's deepest puzzles might share a common root we have not yet found. For now, they rest side by side, each one a reminder that the most precisely tested theory in the history of science is still incomplete, that the universe contains more than we have learned to describe. There is something quietly humbling in that. The standard model can predict the behavior of an electron to more decimal places than almost any other measurement in science. It has been tested in accelerators, in cosmic rays, in the spectral lines of distant stars. And it holds. It holds with extraordinary precision. And still, it cannot tell us why we are here. It cannot account for the extra matter that survived. It cannot name the dark substance threading through every galaxy. It cannot explain the force that is pulling the universe apart. The theory is a triumph, and it is unfinished. Both things are true at once. And somewhere in the physics that lies beyond it, in the particles not yet discovered, in the symmetries not yet measured, in the experiments not yet built, the answers are waiting. Quietly. The way all answers wait. Not announcing themselves, not rushing toward us, simply existing in the structure of things, until the right question is asked in the right way at the right moment. And perhaps that is enough to rest with, for now. The universe kept a secret at its very beginning. A small, precise, extraordinary secret. It treated one particle in a billion differently. It let that particle survive while everything else canceled out. And from that survival came hydrogen, and helium, and stars, and carbon, and planets, and the long, slow unfolding of complexity across 14 billion years. All of it resting on a margin so thin it barely existed. All of it here because of something the weak force did, in a way we still do not fully understand in the first fraction of the first second. And the question of why, the real why, the deep why, is still out there, waiting in the dark between the equations, patient as the universe itself. There is a symmetry that physicists once hoped the universe would honor. It is called time reversal symmetry, and it carries a quiet, almost poetic idea at its center. The idea that the laws of nature do not prefer a direction, that a film of the universe played backward should look just as lawful as the same film played forward. In many ways, this holds. Drop a ball, and the equations that describe its fall work equally well in reverse. Two particles collide, exchange energy, and scatter. Run the mathematics backward, and nothing breaks. The universe, at the level of individual interactions, seems indifferent to the direction of time. And yet, it is not perfectly indifferent. The same experiments that revealed CP violation, the subtle difference in how matter and antimatter behave, also revealed that time reversal symmetry is not exact, that certain particle decays, when examined carefully, do not look the same running forward as they do running backward. The asymmetry is small, it is precise, but it is real. And this matters in a way that reaches far beyond particle physics. Because the arrow of time, the deep, irreversible fact that the past is fixed and the future is open, that you remember yesterday but not tomorrow, that things age and do not unage, that arrow is connected, at some fundamental level, to this asymmetry between matter and antimatter. The two are woven together. We do not yet understand exactly how. The connection runs through thermodynamics, through the initial conditions of the universe through the mathematics of quantum fields in ways that physicists are still tracing. But the direction of time and the survival of matter are not separate mysteries. They are, in some sense, the same mystery, seen from different angles. Time flows one way, matter survived. And both of these facts point back to the same first moments, the same broken symmetry, the same quiet preference the universe had for one particle in a billion. That one particle in a billion. It is worth sitting with that number for a moment, not rushing past it, just letting it settle. For every billion matter particles that existed in the early universe, there was a corresponding billion antimatter particles, and when they met, they canceled. Perfectly, completely, without remainder. A billion became nothing, became light, became energy spreading outward into an expanding space. But one survived. One particle in every billion had no partner to cancel it. One particle was left standing when the annihilation was finished. And that particle, that single, unremarkable, statistically improbable survivor, is the ancestor of everything that followed. Every star that has ever burned in the night sky is built from those survivors. Every planet that has ever formed around a star. Every grain of dust drifting through the space between galaxies. Every ocean, every mountain, every living cell. All of it descended from the particles that were left over when the great cancellation ended. The universe we inhabit is not the universe that was created. It is the remainder. The residue of an almost perfect annihilation. A thin film of matter clinging to existence after nearly everything was erased. And from that thin film, across 14 billion years, came all the complexity and structure and quiet beauty that fills the cosmos. All of it resting on a margin of one part in a billion. And the light from that annihilation, it did not disappear. Energy is not destroyed, it transforms. And the gamma rays produced when a billion matter-antimatter pairs canceled each other in the first moments of the universe. That energy has been traveling ever since, stretching as the universe expanded, cooling as space itself grew larger, losing energy slowly, over billions of years, shifting from gamma rays to X-rays, to visible light, to infrared, to microwaves. Until today. Today, that ancient light fills all of space. It is called the cosmic microwave background, and it is everywhere, not concentrated in any one place, not coming from any particular direction, simply present in every direction at once. A faint and uniform glow of microwave radiation permeating the whole of the observable universe. Its temperature is roughly 2.7 degrees above absolute zero, almost nothing, the coldest kind of cold. A whisper of warmth left over from an event of almost incomprehensible violence. When you hold a hand up in the dark, microwave photons from the early universe are passing through it, through the walls of this room, through the Earth itself. They have been traveling since before the first stars formed, since before the first atom was assembled, since the universe was less than 400,000 years old. And they are still here, still moving, still carrying, in their precise temperature and their subtle variations, a record of what the early universe looked like, a map of the density fluctuations that would eventually grow into galaxies and clusters in the vast web of structure that fills the cosmos today. The cosmic microwave background is the oldest light we can observe. It is the cooled afterglow of the matter-antimatter annihilation that built this universe. And it is, in a sense, the light of everything that was lost, the photons that remain where the particles did not. And then there is you, lying here in the quiet. Every atom in your body is a survivor. The carbon in your cells, the oxygen in your lungs, the iron moving through your blood, All of it was forged in stars. Yes, but before the first atom was assembled, the matter that would eventually become those atoms had to survive the first second. It survived because of that asymmetry, because of the 1 in a billion margin, because the weak force, in ways we still do not fully understand, treated matter and antimatter slightly differently in the first fraction of the first second of time. Your existence is not incidental to that story. You are that story. You are made of the particles that were not canceled, the survivors of the great annihilation, the remnants of a symmetry that was almost perfect, but not quite. And the fact that it was not quite perfect, the fact that the universe had this small, precise, extraordinary preference, is the reason there is anything here at all to wonder about any of this. The universe could have been a sea of photons, uniform, featureless, expanding forever in perfect symmetry, with no matter, no structure, no chemistry, no time in any meaningful sense, just light cooling slowly in an empty and undifferentiated space. Instead, there is this: stars burning in the dark, planets turning slowly around them, and somewhere on one of those planets, a mind that evolved over billions of years, lying still in the quiet, listening to the story of how it came to exist. The margin was 1 in a billion, and the margin was enough. Everything you have ever seen, everything you have ever touched, every thought you have ever had, all of it is the consequence of that margin. All of it is the universe's remainder, shaped by time and gravity and chemistry, into something that can look back at its own beginning and ask why. The answer is still forming. Somewhere in the mathematics not yet written, in the experiments not yet run, in the symmetries not yet measured, the answer is taking shape, slowly, patiently, the way the universe itself moves, without hurry, without announcement. And for now, that is where it rests. In the quiet between what we know and what we do not. In the same dark that holds the cosmic microwave background and the remnant matter, and the long, patient question of why anything survived at all. You are part of that question, and you are, in the most literal sense, part of the answer. The universe does not rest. Even now, as you lie still, everything is moving. Not just the ordinary motion of planets around stars, or stars drifting through galaxies, but something larger, something that operates on a scale so vast it is difficult to hold in the mind without letting it soften into feeling rather than thought. The Milky Way is moving. Not spinning, though it does that too, but moving, carried along with hundreds of other galaxies, all of them flowing in the same direction, drawn by something enormous that sits roughly 250 million light-years away. This region is called the Great Attractor. And the name, for once, is not an exaggeration. It is a concentration of mass so immense that it bends the paths of galaxies the way a stone bends the surface of still water. Except the stone here is a structure hundreds of millions of light-years across, and the water is the fabric of space itself. Our galaxy and the local group it belongs to, and the larger Virgo supercluster surrounding that, all of it is drifting toward this region at roughly 600 kilometers per second. That is not a speed that registers easily. 600 kilometers in 1 second. And yet, because the distances involved are so immense, this motion is invisible to ordinary observation. The stars above you tonight look fixed. They are not. For a long time, astronomers noticed something strange in the data. Galaxies in a particular direction of the sky were moving in ways that could not be explained by the gravity of anything they could see. There was a pull, a consistent, measurable pull, coming from a region that appeared, from Earth, to contain very little. The reason for that apparent emptiness is one of the more quietly humbling facts in observational astronomy. In that direction lies what is called the zone of avoidance. It is not a place where galaxies are absent. It is a place where our own galaxy gets in the way. The dense disk of the Milky Way, its dust, its gas, its billions of stars, lies directly between us and that region of sky. The light from whatever is behind it is absorbed, scattered, obscured. We are, in a sense, looking through a frosted window at something enormous on the other side. For decades, the Great Attractor was inferred rather than seen. Astronomers could measure its gravitational influence on the motion of galaxies across hundreds of millions of light years, but they could not look directly at it. The zone of avoidance hid it. This is one of the stranger positions science sometimes finds itself in, knowing something is there, knowing roughly how massive it must be, knowing the direction and the pull, then still not being able to see it clearly. It is a little like feeling the warmth of a fire through a wall. You know the fire is real, you can measure the heat, but the wall remains. In recent decades, astronomers have found ways to peer through that wall, not with visible light, which the dust absorbs, but with radio waves and infrared radiation, which pass more freely through the obscuring material. What they found confirmed the pull was real and complicated the picture considerably. The Great Attractor is not a single object. It is a region, a broad concentration of mass centered roughly on a structure called the Norma cluster, a dense gathering of galaxies bound together by their mutual gravity. But the Norma cluster alone is not massive enough to account for everything. Behind it and around it lies a larger structure still, a supercluster of galaxies called Laniakea, a name drawn from the Hawaiian, meaning immeasurable heaven. Laniakea was mapped in detail only in 2014, and its scale is difficult to absorb quietly. It spans roughly 500 million light years. It contains the mass of 100 million billion suns, and the Milky Way sits near its outer edge, on a long, slow inward drift toward its gravitational heart. The Great Attractor, in this picture, is not so much a single destination as a region of convergence, a place where the flows of many galaxy groups and clusters all tend, drawn by the accumulated gravity of everything gathered there. And yet, even Laniakea is not the end of the story, because Laniakea itself is moving. It is being drawn toward an even larger concentration of mass, a structure called the Shapley supercluster, which lies roughly 650 million light-years away and represents one of the densest concentrations of galaxies in the observable universe. So the motion is nested. The Milky Way moves within the local group. The local group moves within Laniakea. Laniakea moves toward Shapley, and all of it is embedded in the larger expansion of the universe, which carries everything outward at the same time. These two motions, the local gravitational pull inward and the cosmological expansion outward, exist simultaneously, pulling in opposite directions across different scales. On small scales, gravity wins. Galaxies cluster, superclusters form, matter gathers. On the largest scales, expansion wins. The universe grows, and the most distant structures recede faster than gravity can reach them. The Great Attractor sits in the middle of this tension, close enough that gravity still dominates, but embedded in a universe that is, on the whole, pulling everything apart. There is something worth sitting with in that. The same universe that drew matter together in the first seconds, that allowed the tiny surplus of matter over antimatter to survive and clump and cool and form, is also, slowly, gently, pulling everything apart again. Not violently, not suddenly, but persistently, over timescales so long they have no human analogy. The expansion will not reach the great attractor for an immense time. For now, the drift continues, the slow fall of hundreds of galaxies toward a common center of gravity, a motion that has been underway for billions of years and will continue for billions more. And we are part of it. Every atom in your body, each one a survivor of that first-second asymmetry, is moving through space right now, carried along with the Milky Way, drawn toward a concentration of mass 250 million light-years away, embedded in a supercluster 500 million light-years across. You are not still. Even in the quietest moment, even in the dark of a room where nothing seems to move, you are part of a current that began in the first moments of the universe, when matter and antimatter annihilated, and the remainder was left to drift and gather and cool. That remainder formed hydrogen. Hydrogen formed stars. Stars forged heavier elements and scattered them. Gravity gathered the scattered material into new stars, new planets, new arrangements of matter. And gravity, on the largest scales, is still gathering, still drawing the remnants of that ancient annihilation toward common centers, building structure in the dark, shaping the universe into something with texture and form rather than uniform emptiness. The great attractor is part of that shaping, a quiet, enormous, mostly hidden engine of structure, pulling without announcement, working across distances that light takes hundreds of millions of years to cross. We found it not by seeing it, but by noticing that things were moving in ways that required it to exist. That is, in its own way, a kind of patience. The patience of observation, of noticing small deviations in the motion of distant galaxies and following the logic of those deviations to their source. The universe left a signal in the motion of matter, and slowly, carefully, we learned to read it. The reading is not finished. The zone of avoidance still hides much of what lies behind it. The precise mass distribution of the great attractor region is still being mapped. The relative contributions of Laniakea and Shapley to the overall flow are still being measured and debated. The picture is clearer than it was, and less complete than it will be. That is where the science rests tonight, in the careful, unhurried work of mapping a universe that does not hold still. And you can rest there too, in the motion, in the drift, in the long, slow current of everything moving together through the dark. There is something quietly extraordinary about the fact that you exist. Not in the way that phrase is usually meant, not as comfort or poetry, but as a statement of physics. Because the universe, in its first fraction of a second, tried to erase you. It tried to erase everything, and it almost succeeded. In the beginning, in the first moments after the Big Bang, the universe was not made of matter alone. It was made of matter and antimatter in nearly equal measure. For every particle of matter that flickered into existence, a mirror particle flickered into existence alongside it, identical in mass, opposite in everything else. And when they met, they canceled. Both of them gone, converted entirely into light. This was not a slow process. It happened everywhere, continuously, in a universe so hot and dense that particles were being created and destroyed faster than any clock could measure. Matter and antimatter in constant thermal equilibrium, a churning plasma of creation and annihilation. and then the universe cooled. As it cooled, pair production slowed. The energy was no longer sufficient to keep conjuring new particles from nothing. The creation stopped, but the annihilation continued until almost everything was gone. Almost. For reasons that physics has not yet fully explained, for every billion matter-antimatter pairs that canceled each other out, one single matter particle was left over. One out of a billion. That remainder, that tiny, improbable surplus, is everything. Every star, every planet, every grain of dust drifting between galaxies, every atom in your body is part of that 1 in a billion remnant, the fraction that survived when everything else became light. The light from all that annihilation still exists. It did not disappear. It cooled as the universe expanded, stretched from gamma rays down through infrared and into microwave frequencies. And today, it fills all of space as a faint, uniform glow, the cosmic microwave background, the cooled afterglow of a universe that nearly erased itself in its first few minutes. We can detect it. We have mapped it in extraordinary detail. It is, in a sense, the oldest light there is, a record of the moment matter won, by the smallest of margins. The particle that was not canceled out, the antiparticle of the electron, was the first piece of antimatter ever identified. It is called the positron, and it was found in 1932 by a physicist named Carl Anderson, who was studying the trails left by particles passing through a cloud chamber. He noticed something strange, a particle that curved the wrong way in a magnetic field, not to the left, as electrons do, but to the right, same mass, opposite charge. A mirror image moving through the detector as though it had arrived from some reflected version of the world. It had been predicted. 2 years earlier, Paul Dirac had written an equation describing the electron with such precision that the mathematics itself implied a twin must exist. A particle of opposite charge, identical in every other way. Dirac's equation did not merely describe what was known. It required something that had not yet been seen. And then it was seen. Antimatter is not a theoretical abstraction. It is real. It has been created in laboratories, detected in cosmic rays, and used in hospitals. PET scanners, the imaging machines that map metabolic activity inside the body, work by detecting positrons. The body is injected with a mildly radioactive compound, and as certain isotopes decay, they emit positrons. Each positron travels roughly a millimeter before it meets an electron, and both vanish in a small burst of gamma rays. The scanner detects those gamma rays and reconstructs an image from the geometry of the annihilation. Antimatter, in this way, has become a medical instrument, a tool for seeing inside living tissue, made possible by the same physics that governed the first second of the universe. The human body also produces positrons naturally from the slow decay of radioactive isotopes present in bone and tissue. Each one travels its millimeter, annihilates quietly, and is gone. You have been producing small amounts of antimatter your entire life, without noticing. When a particle meets its antiparticle, both are converted entirely into energy. No mass remains. The conversion follows Einstein's equation with perfect efficiency, more completely than any other process in nature. A single gram of antimatter annihilating with a gram of matter would release roughly the energy of a large nuclear weapon. Not because antimatter is exotic, but because mass energy conversion, when it is total, is extraordinarily concentrated. Storing antimatter is another matter entirely. Any contact with ordinary matter causes immediate annihilation, which means antimatter cannot touch the walls of any container. At CERN, Physicists suspend antiparticles in vacuum using carefully shaped magnetic and electric fields, holding them away from all surfaces. The largest quantities ever trapped this way are measured in hundreds of atoms, an amount so small it would be invisible to any instrument not specifically designed to detect its annihilation. Antihydrogen, a single antiproton orbited by a single positron, was first created in 1995. It survived for nanoseconds before touching the walls of its container and vanishing. By 2011, the Alpha experiment at CERN had extended that lifetime to over 1,000 seconds, long enough to begin asking questions about its properties. In 2023, they confirmed that antihydrogen falls downward under gravity, just as ordinary hydrogen does. The question of whether antimatter might fall differently, whether it might, in some sense, be gravitationally repelled, had been open for decades. The answer, as far as current measurements can determine, is no. Antimatter and matter respond to gravity in the same way. The spectral lines of antihydrogen, the precise frequencies of light it emits, appear identical to those of hydrogen, within the limits of current measurement. If they differed, it would mean the laws of nature are not symmetric between matter and antimatter in a way that no existing theory predicts. So far, they do not differ. The symmetry holds. And yet the universe is made of matter. This is the tension at the heart of the problem. The laws of physics, as we understand them, treat matter and antimatter with near-perfect symmetry. And yet the universe chose matter. Something broke the symmetry. Something tipped the balance by 1 part in a billion, and we do not fully know what. The physicist Andrei Sakharov identified, in 1967, 3 conditions that must have been met for matter to come to dominate. The laws of physics must treat matter and antimatter differently in at least some interactions. The universe must have passed through a period of thermodynamic imbalance, and the number of matter particles must not have been perfectly conserved. All 3 conditions appear to have been met. We have even observed the asymmetric treatment of matter and antimatter directly, in the decay of particles called kaons and B-mesons. The asymmetry is real, measurable, confirmed. But it is not large enough. The CP violation measured in laboratories accounts for only a fraction of the asymmetry needed to explain the universe we observe. There must be other sources, other processes, perhaps involving neutrinos, which are extraordinarily difficult to study and may violate the symmetry in ways not yet measured, perhaps involving physics beyond what the standard model describes. The answer is somewhere, waiting in data not yet collected, in experiments not yet built. The matter-antimatter problem sits alongside dark matter and dark energy as one of the 3 great open questions in cosmology, 3 deep silences in our understanding of the universe, 3 places where the map runs out. And yet, here you are, a remnant, 1 part in a billion that was not canceled, built from quarks that survived their antiquarks, from atoms that have existed in various arrangements for billions of years, passing through stars, through dust clouds, through the slow chemistry of a young planet. You are what the universe kept after everything else became light. You remained, and now you are still breathing slowly, drifting. The universe around you, vast and mostly dark, still carrying the faint warmth of that ancient annihilation, still glowing very softly in every direction.